Okay, we should be live. Let's see if this is working. If it is working, hi guys. Okay, let's see. All right, if you guys can see me, just type something in the chat over here, just so I know that you're seeing this. And we'll get started in a minute, once I mute all of these things. Again, if you guys are there, just type something in the chat so that I know you're there. Make sure you guys can hear me. And we'll get started in a couple. And I'm going to ignore you guys with one last remind right now. Let's see. Oh, it won't let you chat unless you have your own channel. Okay, that's cool. Thank you, Nayeli. So, in that case, if you guys want to chat with me while we're doing this, just send me a message or remind. I have that open. So that totally works too, to ask questions or anything like that. But hopefully you guys can at least hear me. So what we're going to start with is this. I went through, and the 4 basic topics that are going to be on the test are curve sketching, tangent line approximation, optimization, and related rates. And a couple people did send me specific questions that they had, so we're going to work on those today. So generally we're going to work on curve sketching with a general overview and then second derivative tests. We're going to work on tangent line approximations, optimization, and specifically I had some questions about optimizing distance. I know that gets confusing, especially with those derivatives. And then we're going to talk about related rates. So we'll probably break this up over about an hour. If you feel like you're an expert on curve sketching and you want to leave and then come back, feel free to do that. I will be here, and this will be up in like a live stream when you guys are done. So if you don't want to watch it now and you want to be able to fast forward later, that's fine. So without further ado, we'll kind of get into this. We're going to start by talking about curve sketching, and the first question that I got was for just like an overview. And so this is a sheet that you guys have gotten before, but I wanted to go through a couple of these things again and just highlight them and make sure we had an overview of what the important things to know were. So first and foremost, the most important thing with curve sketching, besides knowing what you're doing, is actually knowing the justifications. And so you need to make sure that once you've made your justification, stop writing. Don't write anymore after that. You're good. Sometimes you can write too much and wind up writing the wrong answer. That's really important here. Another important thing is not to mix your explanations. Make sure you're clear on what each thing says. So if you're saying a function is increasing, then you want to say like f prime is greater than 0, but you don't want to say, you know, mix those things and write one instead of the other. The last thing is, please don't write the function, the graph. Be very specific in what you guys mean. And that's important, okay? So I'm just going to pop these up on the screen for a second, and I'm going to answer a couple of reminds that I just got. So take a second, look at those, and then I'm going to kind of go through them with you guys and see if you want, or if you have questions. People can't find the link. Okay, I'm going to send another link. Hold on. Let's see if this one works. And I should put the link in there. This is the first time I've done this when trying to link my iPad into it, guys, so thank you for bearing with me so that we make sure we can actually like do some math in here. Okay. Let's make sure that's working. Okay, so while we see if a few more people can pop on, I've got 5. We got more coming. Okay, so curve sketching, let's just kind of do a brief overview with this. So looking at this, this is really the keys here. The things we're going to be looking at are increasing and decreasing, maxes, mins, points of inflections, and then concavity. When I talk about curve sketching, those are the 3 things I'm talking about. So make sure that those are the things that you're keeping in mind. The first derivative is always telling me about increasing and decreasing. From that, I can figure out more about mins and maxes, but at least the increasing and decreasing part comes from that. The second derivative is always telling me about concavity. So keep that in mind. What you're looking for will depend on what derivative you're looking at. So for first derivative, when f is increasing, I'm looking for f prime to be greater than 0. And notice in this, we're including the interval, right? And we're including the functions. We're not saying it in there. Additionally, if f is decreasing on a particular interval, we're saying that f prime is less than 0. So keep those in mind. And those are pretty much it for increasing and decreasing. For mins and maxes, this is when we get into a little bit more nitpicky. So there's going to be a relative minimum when we have f prime changing signs and specifically going from negative to positive. And that's because my slope is going from negative to positive. And that makes a minimum on my graph right there, right? I'm going to have a relative maximum when I'm talking about going from positive to negative on the first derivative, because my slope would be going from positive to negative, which creates that maximum. Okay. Points of inflection we'll talk about in a second, but let's talk about relative mins and maxes if you just had the second derivative, because this kind of goes back to what we know about concavity. So there will be a relative minimum if we know that, first of all, there's a critical value. So f prime of x, or f prime of, let's say, a, equals 0, or dne, right? We need there to be a critical value there because that's our candidate for a max or min. And, come on, iPad, and the function is concave up, right? Because that's going to have a minimum on the graph. The function will be concave up when f double prime is less than 0. Okay, so when you think concave up, think f double prime, or sorry, greater than 0. So when you think concave up, think f is greater than 0, right? That will be a minimum. There will be a maximum. I can tell the same way. I need there to be a critical value, which means either the derivative equals 0 or the derivative does not exist. Both are candidates. And there is a concave down interval there. So we would say f double prime is less than 0. So that's what I'm working with right here. F double prime greater than 0, concave up, means it's a min. F double prime less than 0, concave down, means it's a max. Okay? And so that ties into concavity pretty well. We'll talk about that in 1 second. Point of inflection is where concavity changes. So point of inflection is not just where a function has a 0 of its second derivative. It is actually where concavity changes signs. And so you need to demonstrate this in what you do, right? When you're proving something with curve sketching. That's really important. And so you'd want to show either that it changes from negative to positive or positive to negative. Concavity, we need to make sure we're thinking about the second derivative, but sometimes we're starting with the first derivative. So the second derivative, okay, it's concave up when f double prime is greater than 0. So it's going to look like this, concave up like a cup, right? When f double prime is greater than 0. It's going to be concave down when f double prime is less than 0. Most of us have those memorized. Most of us do okay with that. But the issue with this comes when we're given the first derivative, right? Especially if it's not a function that we can take a derivative of. So you have to think about the second derivative is the first derivative's derivative, right? So f double prime is f prime prime. When would that be positive? That's my question. When would the derivative of something be positive? Well, that would be when that thing has a positive slope, right? So f prime will have a positive slope, or f prime will be increasing, which would make my second derivative positive because its slope is going uphill. When would f double prime be negative? That would mean f prime is decreasing, and that would make your second derivative negative. So remember that f double prime is really just the slope of f prime, right? And so if you think about that, as long as you know those basic increasing, decreasing rules, you're going to be okay with those, okay? All right, I would like you guys, if you have any general questions about that, either shoot them to me in the chat or on the remind. And I'm just going to pick a couple questions to look at. I don't want to spend crazy amount of time on this, but this was a topic that we had a lot of questions on. So in the next couple minutes, shoot me questions on any of the general stuff, and then we're going to look at a couple questions to see where we'd start with these. So I'm just going to choose a couple. This whole document that I'm doing right now, I will put on my site after this so you guys can access it. But let's start with something like number 1 here. So when would this have a point of inflection? The reason I put this first is because this is one of the most commonly missed things. What we need is we need for f double prime not just to equal 0, but to actually change signs, right? In order to find a point of inflection, we actually need to change signs there. So the first thing I need to do is find that. And so it would actually be y double prime here. So if y is x cubed minus 6x squared, then y prime would be 3x squared minus 12x, and y double prime would be 6x minus 12. So I know I'm looking at my second derivative here, and that's going to be what I use to determine concavity. So set that equal to 0 to find where that function will equal 0. It will never be undefined, so don't worry about that. So I'm going to get that this equals 0 at x equals 2. So now I want to figure out the equation of the tangent line there. First, let's prove that this is actually a point of inflection. So on my sign chart, which again we know is not counting as work, but it at least counts as something there, right? It's helping us guide our thoughts, but you still need to have an explanation on a free response. If I plug in a number less than 2, I get a negative. If I plug in a number to the right of 2, I get a positive. So because the second derivative changes signs here, that's the point of inflection. Now, actually finding the tangent line, well, this is going to be my x-coordinate. I need a point there and a slope there. So I'm going to do y minus blank equals m times x minus blank. I know my x value is 2. If I plug in 2 for y, so into my first derivative, I would wind up with, let me change colors here, y equals 8 minus 6 times 4, 24. So that's negative 16. So this is going to be plus 16. And then your slope is going to be your first derivative there, right? So I would plug 2 into this. So y prime would equal 3 times 4, which is 12, minus 12 times 2, which is 24. So my slope is negative 12. And then I could distribute that to get my correct answer there. Okay. I don't see any huge questions there. Okay. So let's look at another one here. Let's look at one like number 6. So this one you guys can't see the top of. Now you can. Okay, suppose the derivative of f has the graph shown to the right. So this is my derivative function. Which of the following could be the graph of f? Okay, so remember that this, in my mind, should make me think slope. Right? This is the slope of the function. Now you guys can see that. So I know a couple things about my slope. Number one, if I wanted to make a sign chart for this, f prime, I could look at this slope and say, well, where does it equal 0? It never does. This slope never equals 0. So this would be positive the whole time. So I know that f always has a positive slope. That helps me narrow some things down, right? So now if I look at these, okay, it can't be A because this whole region has a negative slope. It can't be B because this whole region has a negative slope. Or, sorry, that's positive. This region right here has a negative slope. It can't be C because this region has a negative slope. It could be D, that's always positive. And it could be E, that's always positive. So both of those are options for me right now, right? Both of those could possibly work. So now, okay, how do I narrow it? Well, we need to look at concavity here. So I made my sign chart for f prime right over there, and it didn't ever change signs. So now I'm going to make a sign chart for f double prime. And remember that f double prime is the slope of f prime. So, bringing this down, the slope of f prime, this is increasing here. This is decreasing there. So f double prime switches at 0. It would be positive to the left of 0, negative to the right of 0. What this tells me here is anywhere my second derivative is positive, this is concave up. So right here, this interval is concave up. And then consequently, I can think, okay, my other one is concave down, right? So that interval there would be concave down. So with that in mind, let's think about it. We know to the left of 0, it needs to be concave up. That to the left of 0 is concave down. No bueno. So that's how I know it must be E. So thinking about those definitions really helps us connect which graph should go with which. Okay. So again, if you have questions, send them to me as we're going. Let me pick maybe one more of these and then we'll go into some other stuff. Okay, let's look at this free response because this is one where we actually need to do some justifying and promise you're going to have to do that tomorrow. So first of all, this is the graph of the derivative of f. I always try to figure out, first of all, what is my graph a graph of? Okay, that's really, really key when you're doing this. So knowing that this is the derivative, I know that this tells me about the slope of f, this tells me about increasing and decreasing, and I can go from there. Some people find it really helpful here to actually start out by just making sign charts. So I could say, okay, for f prime, let's look at this. This is f prime, right? This is the graph of f prime. And it equals 0 at -3, at 1. So I'm going to have turning points at -3 and at 1. Or at least points where it equals 0, right? Critical values. To the left of -3, it's below the x-axis. So that's negative. To the right of -3, it's also below the x-axis. So that's still negative. And then to the right of 1, it's above the x-axis. So that's positive. So this helps me answer a bunch of questions right off the bat, right? Because I can say, okay, f prime tells me about increasing and decreasing. F prime tells me about mins and maxes. So for what values is f increasing? That's my first question. Well, f is increasing when f prime of x is greater than 0. That's my justification. So if you connect that in your head with this is what I want to see, look at f prime and see where that happens. I see f prime is greater than 0 right here. So I'm going to go from 1 to, remember to always look at your domain, 4. And it would be from 1 to 4 because f prime of x is greater than 0 on that interval. This is a totally adequate justification. You don't need more than that. Okay? When does f attain its relative minimum value? So f attains its relative min when we're thinking about going, okay, min negative to positive. And so I would be looking at where I see f prime change from negative to positive. That is at x equals 1 because f prime of x changes from negative to positive. And it's really important here that you don't just say changes signs, right? Specifically, we need negative to positive, okay? Find all values where f has a relative maximum. In this case, f does not have any relative maximums. No relative max because f prime of x never changes from positive to negative. Now, by EVT, there would still be an absolute max, but we weren't asked to find that. And then the last question here that we're going to deal with is, for what values is it concave up? Okay, so concave up. We're looking at the second derivative. So I'm going to go back and make a sign chart for this, actually. So for my second derivative, I'm going to erase some of these babies. For my second derivative, let's change colors here. I'm looking at the slope of f prime. Okay, the slope of f prime. So I'm going to look at the slope of f prime. From -4 to -3, I see that it's increasing. So I'm going to put a mark at -3, and I'm going to put positive because my slope is increasing. Okay. From -3 to -1, the slope is decreasing. The slope is negative. I shouldn't say decreasing. So this would go to -1. Slope is negative. From -1 to 3, it is increasing. And from 3 to 4, it is decreasing. So my periods of increasing and decreasing, I go increasing, increasing, decreasing, decreasing. And so concavity, right, concave up, you're looking for where the second derivative is positive. So my concave up intervals would be -4 to -3. Union, or you can just write and, -1 to 3. Because f prime of x is increasing. And remember, that means, therefore, f double prime of x is greater than 0. Okay, Nayeli just asked, are we going to have theorems on the test tomorrow? Any of those existence theorems? No existence theorems on the test. You need to be able to do your curve sketching basics, first derivative tests, mins, maxes, all of that stuff, concavity, and then all of the application stuff we've done since. So no theorems. Okay, the last curve sketching question that I got specifically was about the second derivative test. So I want to talk about this. Second derivative test determines extrema. Expect at least one question just on second derivative test tomorrow. So second derivative test, think second derivative, think concavity, right? So first thing I'm going to think about is, with concavity, if the second derivative is positive, that means that the function is concave up, which means I have a minimum. We talked about this before. Second derivative is negative. That means it's concave down, the original function, which means it's a max. And second derivative is 0. The test is inconclusive, and you'd have to go back to the first derivative test, which would be just the basic sign chart with the first derivative. Again, we can kind of picture this. The key on this that you have to show is that for this to work, you need to know that there's actually a critical value there. So you need to have f prime of c equal to 0. So we always find the critical values and then just plug them into the second derivative. So a critical value, and this is a rookie move here, a lot of people just tell me that it's where f prime of x equals 0, which is true, but it's not the only definition. It's also where f prime of x does not exist. Because remember, mins or maxes can be at turning points, or they can be at like cusps or corners, right, where the derivative wouldn't exist. So remember to look for both of those. I'm going to look at 2 of these. And the first one is just basic, not really a lot of work to do. So the first one says, okay, f of -7 is 6. That's the value of the function. So this is the original, right? This is just my original. And then f prime of -7 is 0. This is my first derivative, right? Which tells me that this is a critical value because I see that that's a 0. I now know that this is a candidate for a max or min, and so now I can go further. Now they give me the second derivative. I see that this is negative, and so that means that my curve is concave down. So I have a slope of 0 and a concave down curve. So to me, what that tells me is that this must be a maximum. So what I can conclude here is that negative 7, 6 is a maximum. It doesn't ask me to justify, and I should put relative in there. It doesn't ask me to justify, so I don't need to. But if it did, you would say because your first derivative is 0 and your second derivative is negative. So let's take a look at this one. Prove using second derivative test that y equals sine x has a min at 3 pi over 2. If we actually just sketch our parent function here, then, okay, does it have a min? Well, sine goes up, comes back down, and goes like that. Here's 1 pi. Here's 2 pi. So I know that at 3 pi over 2 it has a min. We're going to use the second derivative test to show that. Okay? So I'm going to start with this. I know this is my function. First, I want to find the critical values of this. So y prime, derivative of sine, is cos. And I'm going to set that equal to 0. So cos x equals 0. Think about your unit circle here. Right? Cosine is your x value. So cosine equals 0 anywhere x is 0, which would be at 0 pi over, 0, 1, and 0, negative 1, which is at pi over 2 and 3 pi over 2. So x equals pi over 2 and x equals 3 pi over 2. In the general domain of one sine curve, 0 to 2 pi, then we have two critical values. They're only asking me about 3 pi over 2. So what I'm going to do then is say, okay, let's check using the second derivative test that this is actually a min, right? So now I'm going to find my second derivative. So y double prime, well, the derivative of cos is negative sine. And y double prime here would be negative sine of 3 pi over 2. Now, ideally, what we would like to see is that this comes out positive so that we get a concave up function and we can go from there. But what I notice here is that sine of 3 pi over 2 is actually 0, so y double prime is 0. If this had come out to be positive, we'd be done. This tells me that the second derivative test is inconclusive. It doesn't mean it's not a min. We know it is, right? Is inconclusive. So in order to find if it's a minimum, you need to go back to the first derivative test. So you might get asked tomorrow to do the second derivative test or to just say, why is this inconclusive? And that would be something that would be important there. Okay, so that was the major thing that I got questions about today. That's why we spent about a half hour on that. Keep sending me questions on the Remind or on the chat if you want to, totally fine. We're going to move into optimization next, and then we'll talk tangent line approximations and related rates. I actually got the fewest questions on, so we'll do a little bit of that if you guys have specific questions. Okay, so optimization, the big thing that we're talking about is that there's something we want to optimize. And with optimize, I want you to think about a min or a max. These are those Algebra 1 problems you did back in the day where it just wanted you to find the vertex. We've just taken away the value. Okay, Grayson asked, why is the value 0? Okay, let's go back to that. So the value of sine 3 pi over 2, oh, it's not. Haha, thanks, Grayson. So the sine of 3 pi over 2 is actually negative 1. So it would be negative, negative 1, which makes it positive, which is what we wanted. All right, 100 points to Grayson tomorrow. He gets a free 100. So this would be, therefore, sine x is concave up, or y equals sine x is concave up. So y equals sine x has them in there. Thank you. Okay. This is why you guys keep your questions coming. All right, so optimization, mins, maxes, right? And we're gonna have things that limit us, constraints. So, this is one I got a lot of questions about. Finding the point on the curve closest to 4, 0. So, when you think about the point on a curve, okay, it's a curve. Let's kind of look at this. Square root x, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. Kind of looks like that. And it asked me about the point 4, 0. So the question here is the closest point right there? Is there a closer point somewhere like diagonal? That's what we want to check out here. So we want to find something closest, which means we want the minimum distance. Okay, we want the minimum distance. That's the goal there. So, Elias, I'll answer your question in 1 second. Find the point on the curve that is closest to 4, 0. So I want you to think about coordinate points. 4, 0, and x, radical x, right? Because if this is y equals radical x, instead of xy, I could write this as x, radical x. And what I'm going to do is find the distance between those. So distance equals the square root of x minus 4 squared plus square root x minus 0 squared. Okay, so now I'm going to do square root of this. So this is just x squared minus 8x plus 16 plus the square root of x squared is just x. And so what I get is square root x squared minus 9x plus 16. Nope, minus 7x. This is why I don't do homework on days off. Okay, so now what we want to do is minimize this. And all that means is find a derivative, find the minimum. So, derivative of this. Okay, I'm going to take the derivative of this. So this would be 1 over 2 radical x squared minus 7x plus 16 times the derivative on the inside, which is just 2x minus 7. So, looking at this, I want to find the critical values of that. I'm going to look at just my numerator here because I know that this is going to have to be a real number. I know it's going to have to be something on my coordinate plane, right? And so what I'm going to do is I'm going to set this equal to 0. 2x minus 7 equals 0. Because remember, fractions equal 0 when the numerator is 0. So x is going to be 7 over 2, or 3.5. Now, I want to actually test that that is a minimum. So ideally, especially if you have your calculator, you don't even need to really, but you're plugging in a number smaller than that and then a number bigger than that. And the number smaller than that, plug in 0, plug in whatever. This is going to go from negative to positive. So it is a minimum. So since it asked for the point, the x value would be 7 over 2, and the y value would be the square root of that. So what that means is that the closest that I get to this point is not this point, which is what most people would think, but it's actually at about 3.5. That point is actually closer than the one directly to there. And again, mine's not drawn perfectly, but that's the idea. Okay, I'm going to answer a couple questions while you guys are digesting that. Feel free to send me more. You will need your calculator tomorrow. If you don't have one, I have, I think, 4 extra. Don't, bet on that, but at least 4. So I do have some. Other remind questions. Nayeli said, always chain rule for distance formula. Yeah, right? You have an inside and an outside function. The only time I could imagine you not doing chain rule for distance formula is if you had something like, let's say this. So if we had distance formula came out to be just that, right? If it all simplified below somehow, then you could simplify it. But otherwise, chain rule will work. All right. Grayson said, what equation did you plug in for that sign chart? You're always plugging into the derivative because remember that you're looking at the slopes. It will be a minimum if the slope goes from negative to positive. So make sure you're just plugging into the derivative. Plug into d prime. Since I know the denominator would always be positive because it's a square root, then I actually really just plugged into the numerator, that right there. Megan, I saw that you had a question. What equations do we need to know for tomorrow? So you are responsible for every equation except for like volume of a cone, volume of a sphere, but everything else you should know. So any volume of a prism, any area of a two-dimensional shape, perimeter of any shape, really, we should be able to figure out. Those are the main ones. I mean, the main ones we've used are circles, square, rectangle, cylinder, stuff like that. Distance formula I would know, but otherwise that's pretty much it. Technically you're responsible for anything, but volume of cone and sphere they always give you. Jacob said, yeah, so Jacob said, do I only need to look at the numerator and really look at the derivative of the inside? In this case you do, right? Because we're only going to be looking at where the numerator equals 0, because we have a restricted domain for square root x, so that will work. If you're in doubt, you can check the denominator, but you know, we want it to be something that is going to be within our domain. Okay, and I saw one more. Shout out to Ryan, because Ryan wanted a shout out. Ryan N, because I know there's 70 of you. Okay, we're going to look at another optimization problem. Keep questions coming if you have them, okay? So this one says a rectangle is bounded by the x-axis and the y-axis, and the graph of y equals 6 minus 3x. And they gave you a figure, which was nice. What length and width should the rectangle have? So its area is a maximum. As soon as I see this, I know this is optimization, right? Area max. So, okay. So I need to maximize area. So area equals, I know it's length times width. And then the question is, well, how do I deal with that in terms of what they gave me? So what I always do is I think about this. On my picture, I'm going to label this point x, y, right? But instead of x, y, I'm going to say x, and I'm going to write in the expression I have for y. And that's going to help me a little bit, I think, with figuring out what these are. Because now when I know, okay, what's the length of that? Well, that's my x-coordinate. And what's the width? Well, that's my y-coordinate. So my area here is really my length, which is just x, times my width, which is 6 minus 3/4 x. And now really, this is a straight up first derivative test problem. So area equals 6x minus 3/4 x squared. And now I want to maximize that. So I'm going to take the derivative of that, 6 minus 6/4, or 3/2x, right? And set that equal to 0. 6 minus 3/2x. I'm going to subtract 6. And guys, one thing I will tell you about this is 90% of the time these are multiple choice questions. And so doing the sign chart is helpful for you. But if you only get 1 0, then you kind of know that that's going to be your right answer, you know? So check it. If you have a calculator, it's easy to check, but I would just double check that. All right, so I multiplied both sides by my reciprocal here. And so this is going to be 3 goes into 6 twice. So x equals 4. So again, we can check this. We can go put 4 on our test, plug into our first derivative, right? And actually do a sign chart. It's going to be a maximum, so you're going to get positive to negative. And then all I'm going to do is make sure I answered the question. So what should the length and width be? Well, I know x is 4, and that's this, right? That's my length. Well, what's the width? I need to plug that in. So x is 4. I'm going to do 6 minus 3/4 times 4, which would be 3. So my dimensions would be 3 by 4. that would maximize that area. Make sure you're drawing a picture. Often we've seen this with like a parabola, right? Where we had the parabola underneath there. And in these, it was different because your length was actually not just 1x, but 2x. Because if this point was xy, then this point was negative xy, right? So just draw the picture. I think genuinely that will help you guys. Okay, continue to send questions. Just for the sake of time, I'm going to skip 3. This one I have on here, but we can come back to it. But I know people had some questions about tangent line approximations and related rates, and I don't want to keep you guys here for 7 hours. I'm trying to keep it to an hour. And then if people want to hang around and ask me questions, you can. Good question from Leah. She said, you always plug into the first derivative. If you are trying to find a max or min and you have the function, then you will always plug into the first derivative. Because what you want to know, Leah, I'm going to zoom in just right here. What you want to know is where your slope either goes from negative to positive or from positive to negative, right? And the first derivative is going to tell you that. Okay, so tangent line approximation. Let's look at this one. Let's see what Ryan asked. I would rather fight a duck-sized horse than horse-sized ducks. I would rather have one opponent instead of 100. Okay, so f of negative 3 is 4 and f prime of negative 3 is 2. What is the tangent line approximation of negative 3, 1? So, anytime you see tangent line approximation, even if you're not sure what to do, your best bet is to write an equation of a tangent line. A tangent line, think point, think slope. So, this is my point, right? X and Y. This is my slope. So, y minus 4 equals 2 times x minus negative 3. Now, in class, a lot of you guys were taking this and you were trying to manipulate it and then plug in, which is force of habit from pre-calc. So I get that. But don't. It makes your life harder. I don't want to do any math with negative 3.1 that I don't have to. So I'm going to plug that in before I simplify. So I'm just going to plug that in. Y minus 4 equals 2 times. Now when I plug this in, life is good because that simplifies to something really basic. So I get y minus 4 equals 2 times negative 0.1, right? That is negative 2/10 or negative 1/5. So y minus 4 is negative 0.2. Add 4 to the other side, so y equals 3.8. And they're always going to give you numbers that are really, really close. Okay? That's the basics with these. Let's look at one a little bit more interesting. Let's look at one like this. So we know that f of 1 is 4. And for all points fy, the slope, so this is telling you derivative, the slope is 3x squared plus 1 over 2y. Okay? So, part A, find the slope of the graph at point 1. They kind of lobbed this into you, right? So, A, find the slope of the graph at 1. So, I'm just going to plug into this. And I need an x and a y, but I have that, 1, 4, right? So, part A, I'm going to do 3 times my x value squared plus 1 over 2 times 4. So, 3 plus 1 is 4. 2 times 4 is 8. So your slope at 1 is 1/2. So now you have everything you need for the tangent line, right? You have a point from right there. You have a slope. So part B, write the tangent line at 1. So I know my y value is 4. I know my slope is 1/2. And I know x is 1. So I'm just going to plug that in, call it a day. And then I'm going to approximate at 1.2. So again, please don't simplify. It makes your life harder. Y minus 4 is 1/2 times 0.2, right? 1.2 minus 1. And half of 1.2 is 0.1. So y minus 4 equals 0.1. Therefore, y equals 4.1. That's your approximation. Okay. I'm going to skip this one too. It's the same kind of deal. It just uses implicit differentiation. We will come back to it if we have time. But again, I'm starting to see like some numbers dwindle. 45 minutes is a long time. So you guys are awesome for staying. But let's talk about a couple related rates and then I'll hang out a little bit longer if people still have questions. Okay? Okay, so related rates, we're talking 3 specific things. Normally what you're going to see is you are going to be given quantities that are changing. Well, not normally. You're always going to. So a lot of people will ask me, what's the difference between optimization and related rates? In related rates, I'm given a lot of things that are changing at once, right? Versus in optimization, I'm given a scenario and I'm asked to find the optimal of it. I'm not looking at rates that are related to each other. I'm not given any rates. So related rates, you need to be given some rates. The reason that we do the d whatever dt in related rates is because all of these things depend on time. So if they don't depend on time, then we don't need to do a related rate for it. So that's one thing. So I'm going to start with an easier one. So I've got a right triangle one, I've got a man walking away from a light, and I've got a cone. Okay. And a cylinder one too. So we're going to do a couple of these. Again, stop me, send questions if you have them. I am happy to answer them. Okay? All right. In a right triangle, leg X is increasing at a rate of 2 meters per second. Increasing makes me think positive, and 2 meters per second. They were even nice enough to give me names for these. That's X. We'll call that Y, right? So dx dt, they tell me is positive 2. Leg Y is decreasing. Okay, leg Y is decreasing. So if leg Y is decreasing, excuse me, then dy dt is negative something. We don't know what. But we know that the area of the triangle is always equal to 6 meters squared. And Nayeli's asking a triangle question. How to find how fast an angle is changing. Yeah. Actually, I might modify this one to do that because this one's a little bit hard. So let's go over a little bit simpler one about angles changing, and then we can come back to this. Okay. So let's say that I'm given a triangle, and I know that this is X, this is Y. Let's say this is a ladder falling down a building, right? And it's a 10-foot ladder. And I know that it's falling down the building, so dx dt, at 5 feet per minute. Okay? And I know that it's coming out from the edge of the building, dy dt, at 2 feet per minute. And let's make that negative because we know if it's falling down, x is getting smaller, so that should be negative, versus with y, that's getting larger. Okay? So, maybe I want to know how fast the angle is changing. How fast is the angle changing? And I'm going to say theta's right there. When x equals 3 and y equals, or 6. Yeah, when x is 6. Okay, so there's my scenario. I'll recap it again. We are a ladder, we are falling down a building at 5 feet per minute. So it's falling down. That has a negative rate because it's decreasing in length. We are moving the bottom of the ladder out at 2 feet per minute. And I know that I want to know how fast the angle is changing when x is 6. Okay. So what I'm going to look at here is, well, what do I want to know? I want to know how fast theta is changing. So I need some equation that has theta in it. In this case, you can do sine. You can do cosine. You can do tangent. It doesn't really matter which one you do. Typically on problems like this, they may only give you enough information to do tangent or cosine or sine. In this case, I'm going to do tangent just because that is what most of you guys have been doing. And I want to make sure that, we kind of talk about where you might fall into pitfalls. So tangent of theta would be x over y in this case, opposite over adjacent, right? And I want to figure that out when x is 6. So I'm going to start by taking a derivative. So, all right, derivative of tangent, which you need to know, do you hear me, is secant squared theta d theta dt equals, on the right side, you're going to do low d high minus high d low over low squared. Let's say that you had done this with using the hypotenuse. Your d ladder dt would be 0 because that's not changing. But I'm going for the hardest scenario because that's what you guys try to do. So, all right, what do we plug in here? Let's start with this. I know x is 6. They told me that. I need to know y. That seems to be an issue. So I'm going to label some stuff over here. They told me that x is 6. I need to know why. I am a very smart math student. It is why I am on this live stream right now. So I know that in a right triangle, we can use Pythagorean theorem, and this has to be 8. So when x is 6, y is 8. That helps me. That gets me the whole right side of my equation, which you guys can't see. The secant part is what's trickier. So remember, secant theta, yes, you could figure out theta, but let's say you didn't have a calculator. Secant is just a ratio of sides, right? It's the reciprocal of cosine. So if I wanted to find cosine of this, what I would do is I would say, okay, cosine of theta at this very instant is adjacent over hypotenuse, right? So 8 over 10, 4/5. So secant of theta would be the reciprocal of that, 5/4. You don't need to know theta. You just need to plug that in. So secant squared will be 5/4 squared d theta dt equals, all right, now you're going to plug in. So y is 8, dx dt is -5, minus x is 6, dy dt is 2, over y squared, which is 8 squared. And I made up these numbers. I make no guarantees about if this comes out nicely. Okay, so left side is going to be 25 over 16 d theta dt. Right side is going to be -40 minus 12 is -52 over 64. This is going to be gross. And d theta dt is going to be -52 over 64 times 16 over 25. I know that I can reduce this. 16 goes into 64 4 times. Yep. So -52 over 100, which I could reduce more. 2 goes into this 26 times. So -26 over 50. That could reduce more. Yeah, whatever that simplifies down to, something that I don't feel like simplifying, which is why I have an undo button. So, again, we'd simplify that more if it wasn't 8 at night after a long weekend. But, your units are always going to be in radians, right? Unless I tell you otherwise, assume it's radians. So let's cut this baby off so that if people are on the replay, they're not confused. Okay, if you have more questions about those angles one, send them on reminder in the chat. Totally fine. Until I see some more questions, let's do cone or man walking away. What happened to the theta between the green and orange step? Okay, so let's go back to that. That was a good question, Ryan. So he said when you plugged in 5/4, what happened there? So theta here, and I'm just going to look over here. So theta, cosine of theta would be 4/5 because it's 8 over 10 at that instant. And then secant of theta is the reciprocal of that. So that's 5/4. So Ryan, what happened there was I had secant squared theta right here. I just said, well, I know secant is 5/4. So I plugged it. Whoa, Nelly. That was a little large in the charge. I plugged in 5/4 where secant was. So that became squared. Does that make sense? Grayson said, am I more likely to see an open box problem or part of a barn type thing or something with a graph? So I would say generally you're more likely to see something either geometric or with a graph. AP tends towards graphs. So that's how that goes. All right, let me make sure I don't have any other questions on that. I see some votes for cone and some votes for man walking away. I see more cones right now. So we're going to go cone, but we'll come back to man walking away, okay? All right, cone. So I want you guys to be careful of this. Jacob, I see yours. We're going to do that next. So when you see the word funnel, this is a touchy AP thing because I know that when we think about a funnel, what do we think about? We think about a cone. Not all funnels are cones. And that was a pitfall in the AP exam a couple years ago. So just because you see the word funnel, don't assume it's a cone unless you see in the shape of a cone. Okay? So on this one, they tell me it's a cone. Don't make assumptions unless they give you more than that or they say, you know, approximate it as best you can. Okay, so this cone is 30 centimeters deep and has a diameter across the top of 20. First thing I always do is I draw it. So I'm going to start with my radius. I know my diameter is 20, so I'm just going to say that's 10. Save me a little hassle. And I know the height is 30. Before I go anywhere, my immediate thought is to go, okay, I know that the ratio of radius to height is 10 to 30. And then I can solve this whatever way I want, but at least I have that down. Liquid is flowing out of the funnel at a rate of 12 centimeters cubed per second. I look at that and I say that's volume because of the centimeters cubed. So I know dV dt is 12. Should that be positive or should it be negative? Well, my volume is decreasing, right? So that's going to be negative. So, just looking at the chat really quick. Okay. So at what rate is the height of the liquid decreasing at the instant when the funnel is 20 centimeters deep? So I want dH dt, which tells me in my volume formula, try to get all in terms of H. Some of you guys keep doing it by doing product rule every time, which is awesome. Great product rule practice, but you don't need it. So I will give you this formula on the test if there happens to be a cone. Can't imagine that there would be one. I would give you that formula. But I'm going to try to get this in terms of H. So I want to plug in for R. So R is 1/3 H. Right, just cross multiplying. So volume is 1/3 pi times 1/3 H squared times H. And square everything. So volume is pi over 3, I'm getting lazy there, times H squared over 9 times H. So my volume formula is pi over 27H cubed. No calculus yet, right? Just pre-calc. Okay, so from there, I'm just going to move some stuff around here so we have a little bit more space. This is actually how I used to teach every day. I didn't have a smartboard, I just had an iPad. It was awesome. So dV dt equals, bring down the 3, power rule, right? 3 pi over 27 or pi over 9 H squared dH dt. dV dt they told me was negative 12 pi over 9. They tell me the height is 20 here, 20 squared, and they want dH dt. So I have everything I need now. So negative 12 is 400 pi over 9 dH dt. Excuse me. And multiply by 9 over 400 pi is 9 times 12 is 108. Negative 108 over 400 pi. And then check your units, centimeters per second. And again, you can reduce that. I am not, for the sake of, I don't have a calculator. Okay, send cone questions, because that was highly requested. What cone questions do you have? Or any other questions? And then I've got 2 more, and then we'll call it a night. If you guys need to go. It's totally fine. You're not offending anyone. Where can you use the similar triangles in a cone problem? Awesome question. So I actually used those without ever, I snuck them in. It was incognito. So here, what I'm looking at is that I had a ratio of radius to height, right? And I set it up here. I said radius over height is 10 over 30. So this was 10, this was 30, right? Then what I did is I said, okay, now I have a smaller cone in here, or a smaller radius and height. That's R and that's H. Those are your similar triangles. They both have right angles here. This angle is reflexive, if you really want to get into some geometry. And by angle, those would be similar. So the similarity comes from the proportion, or the proportion comes from the similarity. I saw another question. Do we need to simplify the test, or can we leave it like that? If you have a calculator, try to simplify down. If you don't, I care about your right answers. I will tell you in the directions how far to simplify. I would never leave it in, I don't leave fractions in fractions, don't leave decimals in fractions, but generally, you know, if you have 108 over 400, I'll give you credit for it unless the directions state otherwise. Okay, let's do a light one, and then one last one, and then we'll go. Okay. Oh my gosh, so many texts. Okay. A light is on the ground 20 meters from a building. So I already think building. I think that this is 20 meters. And this is my little light. Very lifelike. Okay. A man 2 meters tall walks from the light directly towards the building at 1 meter per second. So my little man, he's 2 meters tall. His height is not changing, so I'm labeling that. And then he's walking towards the building at 1 meter per second. I'm not labeling that directly on the picture because that is not a length, it's an amount. And then how fast is the length of his shadow on the building changing? So think about that. That is actually, I know I'm going a little color crazy here, but his shadow goes to here, right? So this is what I want to know. How fast that length is changing when he is 14 meters from the building. Again, that's not always the same. Okay, so that's 14 at a particular time. So let's see what we can figure out here. So I know that we've got a couple different variables here. The height of his shadow is a variable, so I'm going to call that x. The distance he is from the building is a variable. So is his distance, like, from the light. I'm going to go with his distance from the light here because I don't know that. They don't give that to me at that time, even though I know I could figure it out. Also, this is the side of my triangle, right? This little triangle there. So that's why I picked that for y. But you could choose it another way. So, similar triangles. You've got a little one and a big one. The little one, I'm going to do this, and I'm going to use a highlighter to show you guys this. So I'm going to go bottom leg over perpendicular leg, okay? So this ratio I'm going to do is y over 2, and that 2 doesn't change, right? Equals. Then for the other one, I have to do the same ratio. So I'm going to do this leg over this leg. Now, that distance changes, right? That distance changes. Actually, from the light, it doesn't. That's always 20. So this would be 20 over x, right? So, let me make sure I set this up right. Y over 2. Okay. So, I would have x times y equals 40. So, y equals 40 over x. Or x equals 40 over y. Doesn't really matter. I want to know how fast the length of his shadow is changing. So I actually will probably solve for x because I want dx dt. So now what I'm going to look at is, okay, dx dt equals, now this is y to the negative first. So that's going to be 40 times negative 1, y to the negative second, dy dt. Okay? Then, what do I want? Well, I want dx dt. So 40, negative 40 really. Y to the negative second. So if he is 14 away, then y is actually 6 there. And dy dt, they told me, was 1 meter per second. And that's getting bigger, so that's positive. So this would be negative 40 over 36. Reduce that down, right? 10 over 9. Yeah. So negative 10 over 9 meters per second. And it should be negative because it will get smaller. The closer you get to the building, the smaller your shadow. Okay, a couple other questions as you guys are looking at that, thinking if you have more questions on that. Nick said, does it matter if we write out dv dt or just v prime? I would put dv dt because it matters what we're taking the derivative with respect to. So I would always put that. We'll get into cases later in the year where we're not taking the derivative with respect to time. And then Grayson said, more or less than 15 points. The test is worth more. A few more. All right, last one, and then I will just let you guys ask questions if you have them, okay? So this is kind of a weird one. The height of a cylinder, those have Y's in them, is increasing at a rate of 3 inches per minute. If the relationship between the radius of the cylinder and the height is modeled by that, at what rate is the radius changing when the height is 3? So this one seems like, okay, where do I go? I don't see volume. I don't see dv dt. People get freaked out by this because it's almost too simple, right? So we are going to come back to this problem as soon as I answer Meg's question. Meg said, how did I get y was 6? So on this, they told me that it was when x was 14. And when x is 14, that would mean y is 6 because that whole distance is 20. Hopefully that makes sense. I know it's hard when you don't have like the question right in front of you sometimes to follow all the info. Okay, lastly, we're talking about this one. They give you this function. They tell you radius depends on height. And they want dr dt. And they gave you dh dt. So people will overanalyze a question like this. You have everything you need here. They gave you this formula, right? So what I would have is, okay, r equals h squared plus 3h plus 1. So dr dt equals 2h dh dt plus 3 dh dt. And then just plug in. So dr dt would be 2. They told me h was 3. And dh dt is 3 plus 3 times 3. So 18 plus 6. So dr dt is 24 inches per minute. I know we saved that for last, but sometimes people overanalyze because they think it has to be something harder like these, and it just doesn't. It can be more straightforward. Okay, that's what I have. So I'm going to hang out for like 10 more minutes. If you guys have questions, send them on Remind or send them in the chat. It doesn't matter to me what you do. If you have questions about anything, feel free to do that. And if it's something like you just want to message me on, you don't want me to go over with everybody, that's fine. But the test is 10 multiple choice and 8 free response. It's a mix of everything. You have your calculator for all of it. So yeah, just send me questions. Okay. I'll see you guys later if you're not staying. If you're staying, send questions so I don't just sit here awkwardly. And I will also put this up on YouTube, and I'll put this document up. There's still 11 of you here. People are just waiting for someone to ask a question. If you don't ask, I'm going to show you my giant unit circle. Are you ready for this? This is the best student project I ever got. So you guys need to one-up this. Okay, Grayson said, can we briefly do another optimization problem? Grayson, anything in particular? And then Ryan asked about second derivative on a graph of f. Yeah. So while Grayson is answering that, Ryan will do second derivative on a graph of f really quick. Second derivative tells you about concavity, right? So if the second derivative tells you about concavity, if you're given a graph of f, you're looking for concavity. So let's say I'm given this, right? And this is f. And again, this is going to be a little loosey-goosey because you can't actually like define where these points are, but I'm going to approximate those points right there. So second derivative, what you're looking at is it concave up or concave down? So if this is f, this is concave down here. So this would mean that f double prime is negative. Then it switches to concave up here. And again, I just put those points there. To actually find them, we need calculus. F double prime is positive. And then again, we see that these are concave down. So f double prime would be negative. So Ryan, from there, that's what I would think about. Find things about the second derivative from a graph of f. All right, I see two different questions about optimization. I see parabola, and I see something with like geometry with a barn. So let's start with parabola, and then we'll go from there. We'll do the barn one. So, okay, if you have a parabola, so let's say I have y equals 9 minus x squared, right? You have to think in your head, well, what does that actually look like? What does that function look like? And sometimes it helps to rewrite it. So negative x squared plus 9. So that's going to have a y-intercept at 9 and be a sad parabola. But the nice thing is at least it's symmetric over the y-axis, right? It's an even function. So what I want is I have this rectangle that is inscribed in there, and I want to know the maximum area of it, let's say. So I need a function for area. So I'm going to relabel these points the way I did before. So instead of xy, I'm going to label it as this, right? X, 9 minus x squared. And this one I'm going to say is negative x, 9 minus x squared. So I know that they're xy, but I'm relabeling them to benefit me. So area equals length times width. Think about what those would be here. This bottom side, well, this is from 0 to x, so that's x. This is from 0 to negative x, so that's x. So this whole side length is 2x. Then that's my length. My width here is this height, which is just the height of the function at that point. So that would be 9 minus x squared. So my area function is really 18x minus 2x cubed. So then what we're going to do is say, okay, I want to optimize that. So area, take a derivative, minus 6x squared. And set that equal to 0. We want the critical value. So I'm going to do combining some steps here. I'm going to factor out a negative 6. And so this would be x squared minus 3. And then that would give you x is plus or minus radical 3. So we know it's not going to be minus radical 3 because we're talking about dimensions. So it's going to be positive radical 3. So if I want the dimensions that would give me the greatest area, let's say, then I would say, well, your width would be 2 radical 3, right? 2 times x. And your height would be 9 minus radical 3 squared, which would be 6. So it would be 2 radical 3 by 6. And if it actually asked you what the max area would be, you could multiply those together. Hopefully that makes sense. If you still have questions on that, ask. Okay, Grayson, you said you wanted to do a like barn one. All right, let's come up with one for that. I'm just going to a clean page. Okay, so let's say I want to build a barn. I have 250 feet of fence, or I want to build a fence. And this fence is going to be right on a barn, right? So here's my barn. Could draw lots of little animals in there, but that's my barn. And my goal is to build a fence where it only needs to be 3 sides because the barn is 1 side, right? So I know that I have 250 feet of fence to do that. I want the maximum area. So I would say, okay, this is x, this is x, those are the same, that's y. So the actual fencing here, the perimeter, is going to be 2x plus y. And that's going to equal 250. That's a constraint, right? That is the most fence that I can use. And if I use that whole fence, that's better than not using it, which is why it's inequality. So then area is going to be x times y. And to maximize that, I need to do right area all in terms of one variable. So instead of that, I'm going to do x times 250 minus 2x, because that's the same as y. So then from there, I would have 250x minus 2x squared. And again, I've not done any calculus yet. This is all pre-calc. So from there, I'm going to maximize that. So a prime is 250 minus 4x. Find the turning point for that. So 250 minus 4x equals 0. And that would give me 250 equals 4x. And x equals 6. 4 goes into 10 twice with 2 left over, 62.5. Is that right? I think that's right. So that is my length that would give me the maximum area. Then to actually find my dimensions or my area, so this is x. To get y, plug that back into here. So 250 minus 125, right? And so this would be 125 by 62.5 feet. And then find the actual area, you can multiply those. Okay, so you've got like 3 more minutes and then I'm gonna go. Any last questions? The 7 of you that are still here, I'm proud. You're hanging in there. Anything else? Okay. I'm going to send you guys a quick, like, did you like this or not? Was this helpful? Just let me know. If this was good, we can do it again. If not, we won't. If you have other questions, just send me more reminds, and I will see you guys tomorrow. I'm there before school, and I'm there 1-2 tomorrow if you guys need anything too. Okay? All right. See ya.